Hey y'all, today is the last video where we're really going to learn about the history of atomic structure. In today's video, we're going to look at the current model of the atom, known as the quantum model. Now in AP chemistry, they've removed a lot of the nuances of the quantum model out of chemistry. So there are going to be things you hear in this video that you might never actually need to necessarily apply, but conceptually, they're going to be a big deal. So even though you might not be asked explicitly about some of these things, you are absolutely going to need to understand why and how we have evolved to this model of the atom. So let's go ahead and get started by talking about the quantum model as it pertains to the last model we talked about, the Bohr model. The first thing to understand is that based off the experiments that we've talked about already, we know that the atom has a small positively charged nucleus. We know that there are electrons, which are negatively charged subparticles that surround the nucleus in a very low density cloud. And we know that those electrons exist at various energy levels. The quantum model builds slightly beyond that understanding. So with a quantum model understanding, you will know that electrons do exist in energy levels. However, there are also sublevels, sometimes known as subshells. And within those, there are things called orbitals. So let's start by talking about each of these, and then we're going to discuss how they are actually applied in AP chemistry. The first thing to keep in mind is that valence electrons in AP chemistry are normally the most critical for our purposes. Obviously, all electrons are important, but the valence electrons are going to tell us everything we need to know about reactivity and how different atoms are going to behave in different scenarios. When we look at the electrons, the valence electrons are those on the further out energy level. Basically, the energy level that's on the farthest outside. We sometimes know energy levels as shells, so this could also be considered the valence shell or the outer shell of electrons. Inside of that, there are core electrons. So we have valence electrons are on the outside, and then any electron that's found in the middle below that valence shell, that valence energy level, is considered a core electron. Electrons are always moving. In fact, there's a principle created by Schrödinger that basically says that we always know electrons are moving, and we know either how fast they're going or where they are, but we don't know both at the same time. It's called the uncertainty principle. And the premise of this is saying, okay, well, electrons are always moving, and different electrons have different amounts of energy. In general, the further an electron resides away from the nucleus, the greater its energy. That's in general. There are some nuances to this, okay? But understand this. The further away from a nucleus an electron is, generally speaking, the greater its energy. The problem is, with the Bohr model, all of that lined up only with one atom, hydrogen. See, the quantum model has to build out these things called subshells or sublevels. And there are 4 sublevels, the S, the P, the D, and the F. These are sublevels that you take a single shell and you break it apart into 4 different areas based off of their shape of cloud. You don't need to know this, but I do need to talk about this briefly because otherwise most of the atom won't make sense. The difference between the S, the P, the D, and the F is all about shape. Now, the AP has removed shape from the curriculum. We don't need to know shape anymore. So you don't need to know that an S sublevel is spherical or that a P sublevel looks like a dumbbell. But you do need to understand that electrons do exist within these orbitals. And these orbitals make up sublevels. The S has 1 orbital. The P has 3 orbitals. The D, 5 orbitals. And the F, 7 orbitals. Within each orbital exists 2 electrons. So 2 electrons per orbital, which means that the S sublevel can hold 2 electrons. Each P sublevel can hold 6 electrons. Each D sublevel can hold 10 electrons. And each F sublevel, well, it can hold 14 electrons. So understanding how atoms are built is critical. One thing to keep in mind and this is just, again, a little bit of a nuance that the AP doesn't necessarily expect you to know, is that even electrons that primarily reside in the valence shell can, from time to time, dive in closer to the nucleus. So when we talk about the distance away from the nucleus, what it really is saying is, on average, where is this electron relative to the nucleus? Now, all of what I just talked about is going to apply in a couple of videos when we talk about things called electron configurations. You are going to need to be able to determine how an atom is built based off of its electrons. So, walking away from today, let me remind you, we have periods on the periodic table that we've already talked about in an earlier video. Those periods are based off of how many energy levels an electron or an atom has. So if you're in the first period, like hydrogen and helium, you have one energy level or one shell. If you're in the second, well, then you have two. The third has three. The fourth has four. So take a look at the periodic table for a second. Look for carbon. What period is carbon in? Yeah, it's the second period, right? The second period, that means it's in the second row down. How many energy levels does it have? Yeah, that means it has two energy levels, right? So with two energy levels, that means that it has a core and it has one energy level beyond that core. That's carbon, okay? In the later video, we're going to talk about how to account for valence electrons, how to diagram out these electrons, but it's simply important to understand that when you're thinking about an atom, you gotta know the quantum model. Take a look at aluminum. How many energy levels does it have? Yeah, three, right? It has three energy levels because it's in the third period. That means it has two core shells and one valence shell. That one valence shell is going to be the furthest out away from the nucleus. And again, as I said earlier, it is where all of the important components of reactivity and how the behavior of the atom is based off of how many valence electrons it has. It's all about valence. So again, we're going to talk a little bit more about that later on in this unit. So that wraps up today's video. It was mostly conceptual. Let's do a quick recap. Today we learned the quantum model of the atom, which is our current model of the atom. We now understand that atoms are made of a small, positively charged nucleus containing both protons and neutrons. We know that electrons exist in a cloud that is diffuse and low density surrounding that nucleus. Those electrons are constantly in motion. They are existing in areas called orbitals. Those orbitals make up sublevels. Those sublevels make up energy levels or shells. And in the end, core electrons and valence electrons are going to impact the size and behavior of the atom. So you do need to understand all of this. You do need to be able to think about what an atom really looks like. In future videos, we're going to apply this knowledge and we're going to be able to take this understanding throughout the rest of the year when we're thinking about how atoms behave and, importantly, how that behavior impacts different things like reactions or even batteries, electrochemistry stuff. All right, it gets really interesting really fast. I'd like to thank Anya Vertikova for writing, filming, and editing this video. I'd like to thank you guys for watching it. I hope you enjoyed it, and I'll see you in the next one.